All right, you're live.
All right, cool.
Hold up. You can see chat.
All right, welcome to lecture number 2. We're gonna start by talking about divisibility. It's the notation that we kind of briefed over in the first lecture. You may have been confused about it. It's like if A divides B, that like the straight line. We're gonna talk about that. Then we're gonna go to divisor algorithm and then Béziut's theorem. And we're gonna do part 1 of the proof, and then next time we're gonna do part 2. Part 2 is a lot shorter. I just didn't want to keep you guys here too long.
Sorry, we need a different marker.
Okay.
Also, the eraser.
All right, divisibility. The formal definition of divisibility, I'll write this in your notes. If A divides B, then there exists an integer k such that a k equals b for some k and the real numbers. Okay, it's a lot of jargon. Basically, it's saying like 3 divides 12 because there exists an integer 4, so that 3 times 4 equals 12. Okay. I'll leave this definition up here. All right, let's do an exercise with this just to, continue to build our proof expertise. Okay. I'm gonna prove that if A divides B and A divides C, then A divides A, B plus or minus C. Okay. Okay, does anybody know what we can start? Recall from last time that the best way to start any proof is to focus on the definition. So what do we know about this definition? What can we try to expand on? Yeah, Shiva.
By definition, if A divides B, then B is congruent to 0 mod A.
Mod. Okay, mod. Can you use the definition up there? Before doing mod, we can. That's mod is cool. It's like this definition right here.
A times K.
Yeah. So by definition, let's just set an integer k, ak equals b, and for c do the same thing. Let's do a m equals c. Let's do k and m real integers. Okay. From here, what can we do? Well, we're trying to show that there exists an integer, let's say L, such that AL equals B plus C and AL2 equals B minus C, right? That's our goal. When you do B, let's do B plus C. B plus C from this equals AK plus AM, right? We can factor an A out over here and write this as A times K plus M. And because K is an integer as defined over here, and M is an integer, K plus M is also an integer. So what does this show us? If B plus C equals A times an integer, what's true then? A what?
A divides.
Exactly. A divides B plus C. K plus M is going to be, we can substitute that by some integer. Let's just call it I.
Is it A assumed an integer in this as well?
Mm-hmm. Yeah. Divisibility. Huh?
B and C correct? All elements of R?
Yeah.
So A is just a scalar.
Okay, and then we can do the same with B minus C. B minus C, you can substitute these two, and that's going to equal AK minus AM, just gonna equal A times K minus M. K minus M is also an integer. So A times an integer equals B minus C. So by definition, A divides B minus C because there exists an integer such that A times an integer equals B minus C. All good? Okay, there's good. I'm gonna give you guys an exercise for the class. I'll give you a few minutes to talk with your friends, formalize a proof if you have paper. And I'm gonna go around and check your work. Be ready to be called on, okay? Okay.
Sorry, I didn't catch that last one. Yes.
Hmm.
That's what I'm
I have to wait for today.
I think accepted something slightly.
Huh? Is that always gonna be just like, oh, this is my first year, so maybe next year.
All right,
Yeah.
your proof is if A divides B and B divides C, prove that A divides C. It's transitive property.
Oh, no.
Huh?
Kathir's fine.
Okay.
Kathir's coming?
Maybe.
Why didn't you do that?
Oh, I'm not. So you know, the comments, you have to put hours and weeks.
Hmm.
How long do we have to solve this? Because we need the last part of your first.
Come back.
Hold on, I have the chat
Yeah.
there. Let me just.
What am I supposed
Kind of
to?
over.
You don't have to write everything down. You're good. Okay.
Sorry.
Yeah. What's up?
All you missed is.
Just be ready to explain it. You don't have to write everything down.
That's like the last thing.
That's like an hour 30.
You should show that, that Andrew Wiles.
7 to 8:30.
Sure.
Hmm.
You should show the Andrew, Wiles film for what?
Yeah, we should.
Okay, so if you have A times B,
Oh, Miss Vincent.
A, K, B, and then
Would you get it?
B divides C, and B equals C. Therefore, A divided by C.
Yeah, hold on.
This is
Or junior?
Use stats or.
Yeah, she told me she's also going to run.
MB equals C, for example.
tomorrow.
Yes, and she's for her being leaked by Miss Vincent in HSC apps, which is Alana.
What's up, man? Can I go check?
Yeah.
Where's she at?
Alana's computer science, B hallway, A hallway, kind of all the way.
You gonna come to Charles? Alright.
Well, it was a mistake.
Yo,
And over.
1,001, I treated.
All right. Does let's gather up real
I would have done
quick.
that too if I didn't have, I literally typed in my calculator one of the numbers wrong and it messed up my.
I did 1,000.
All right. That's how you
I
ready?
would-
I realized as soon as I left the door.
That was not.
Bro,
Does anybody want to share their proof?
I could not find the. I swear I got your email and I was checking like the last 5 days and it was just gone.
I'll email you the link. Anybody go with the proof? All right.
Okay, so.
Do you wanna share?
I didn't study.
I got
Okay.
All
All right. Let's quiet down so Will can share his proof.
So this.
All right. Will.
Alright, let's get back to the lecture.
We got our actual scores.
Yeah.
We go to Miss
A
Vincent.
divided B, that means that
It's not
there's
online.
Oh yeah, check your PSAT.
Okay.
Guys, can we use it as B divides C, there's
You should
a
use it.
integral by L
Hey, should I-
such that C
Oh,
equals
he
L
didn't get,
times
he
C,
didn't high score, dude.
right?
You're locking on that.
See, yeah.
So then.
Yeah, he didn't get
Right, whatever.
I thought this guy was gonna get like
So then,
Hey, come
if B equals A.
And now
times
you know what
A,
the expectation
substitute that
is.
in to,
Can you say that again?
B equals A times K, you substitute it into the C equals B times L. So
Okay.
then C equals LKA, and since L and K are both integers, that means that, L times K is also an integer, you can call it M or whatever. So that means that C equals MA, so therefore, A divides C.
No.
Beautiful. All right. Did everybody catch that? All right. So you basically just again using the definition, AK equals B, BL equals C, and then we substitute it in, and because L and K are both integers, L times K is going to be an integer, A times LK is going to be C, and then by definition, A divides C. Okay. So it's transitive. Okay. Now we're going to head on to more complex stuff. So if you're feeling lost, feel free to ask questions. Okay, we're gonna prove.
Are you the kid who did topology like right now? Are you taking?
I did apologize last year.
Why is it ring?
What are you in that?
Oh, BC.
Somebody in DC.
BC. Oh, what are you doing?
BC too.
Wait, what
You
grade
guys
are you
can
in?
take linear algebra
Wait,
second
wait,
semester.
wait.
No, we're not.
Oh,
Do you
it's
want-
T 1500.
Why not?
Yes, it counts.
You really? It counts as
Okay.
calculus AB.
And also it takes up a period. It won't be-
This part of the lecture is going to be a lot more confusing, so I'd definitely take notes on this if you are planning to do this class. It's a live stream, yeah. Okay, so the divisor algorithm states for any integers A and B with B positive, there exists unique integers Q, which is the quotient, and R, which is the remainder,
So he zipped out of here.
such that A equals BQ plus R, and R is a strictly positive integer in between 0 and B. Okay, like always, there's going to be a lot of jargon in the beginning, but this is basically saying that whenever you have two integers, when you divide them, you can express them like this. Okay,
Right?
Yeah.
You wrote your ampersand backwards.
my what percent?
Ampersand.
Okay, let's just do A and B.
Do you know how to write Anderson?
Okay. Let's take two integers A and B. Let's say they're 24 and 5. Okay, let's say 24 equals A and 5 equals B. Okay. How can we write that in this form? 24 equals 5,
Q plus R.
5Q, and what will Q be?
Before, right?
Q will be 4 plus 4. And that works because 4 is strictly less than 5. It's a positive number strictly less than 5. 4 is our remainder, right? When you divide 24 by 5, you can go in 5 times, or 4 times, sorry, and then you have our, I should do this, yeah. And our, the remainder is 4, okay?
That was on ABC's.
No, not that.
I've used mod since fifth grade.
Yeah, modular arithmetic we're gonna cover in probably we're gonna start next week. Okay,
Oh.
all right, there's 2 parts of this proof. All right, we need to prove existence first, and then we need to prove uniqueness. This is very similar to a proof that we did last time, but not really. All right, so proof of existence. All right, let there be a set S.
Why did you bottom it in multivariable calculus?
No.
Okay. Let there be a set S defined by A minus BQ for Q and should say Q and B. Yeah, Q is real. A minus B Q is greater than 0. Okay. We have R equals A minus BQ. Right? And basically, intuitively, we need to show for existence that R is indeed a integer strictly bounded by 0. So our intuitive goal with uniqueness show that R is strictly in between these two. Okay. Now, raise of hands from last class for those that were there. What was your favorite type of proof technique?
Wow.
Proof by contrast.
Contradiction. Yeah. Contradiction is
always fun.
contradiction is by far the most popular type of proof, and we're gonna see it again over here. Okay. So let's
There was another proof I enjoyed.
yeah, what was that?
Those would be induction proof.
Induction is fun as well. Okay. Is it okay if I erase this? Is it good if I erase this?
Yeah.
All right, cool. Okay. All right. So a great technique to start for these more abstract proofs is to define a smallest element of the set. Okay. Elements are really cool because they give you a big domain of numbers with a certain characteristic, right? So S is defined by this. This is a lot of jargon, but it's just A minus BQ, right? Or just R. This set S is for all the integers that could be R, the remainder, right? What's really interesting about this is that, or I guess not that interesting, but it'll help us a lot, is that a list, let's say this set has 1, 0, 3, -3, 4, whatever. What's this? Each set of integers has a smallest and biggest element, right? What's the smallest element in this set?
-3.
-3. What's the biggest?
4.
4. Okay. So do you agree that this set with all of its integers is going to have a biggest and smallest element, right? So let's define one of these elements. In set S, let R be the smallest such integer element. Okay, such that A equals BQ plus R. Okay. Now our goal, not to get lost, is to show that this is true. All right. For sake of contradiction, yes, no?
7-10 on both.
1440.
14-20.
But I don't think my score cuts it.
I don't think I was 14-40.
It might, cause it
No.
it was a hard test, so it might.
This is not
It was the
gonna
math side, bro. I think reading had like a 720, but.
Okay.
Wait,
What do you ask?
you got it?
No.
What'd you get?
14-20?
14.
Okay, 760 math, 710 English. I didn't know the vocab. I'll get it next time.
Okay. For sake of contradiction,
Or what it was last year.
14.
Oh, so probably because.
You're 14. Yeah.
He's 70.
290.
You both.
Yeah, I got a higher reading.
Reading is done.
let
Yeah.
R be greater than or equal to B. Okay. So we need to show that this is not going to be possible. Okay. Let's just do greater than b to make it more simple. Okay. So if there's a contradiction in this from following this this definition, we know that this must be true, right? And then we've proved existence. Okay. Okay. Notice that r minus b, because r is greater than b, is going to be a positive number. And notice that r minus b, by definition, is also going to be less than r. Do you agree? Does everybody agree?
Yeah.
Okay. Let's go back to a equals bq plus r. This is going to be a really clever set of algebraic manipulations that are going to come up, and it's going to be pretty beautiful. Okay. If let's add plus b minus b to both sides of it's the same side, but b minus b. Are we doing anything to really change anything? Or no, right? We're adding b and we're subtracting b. Everybody okay with that? Okay. Now let's factor out this part and do b q plus 1 plus r minus b. Why is this important? Well, what are things that we're not allowed to change? We're not allowed to change a or b, right? Because they're already defined as our integers. And we didn't even change anything. We're just writing it a different way, right?
Right.
But do you agree that this is in the form a equals b q plus r, right? It's in the same form. Let's say let's put knots over here. Do you agree that this is in the same form as this?
Yes.
Right? So let's take this as our new quotient. And let's start r minus b as our new remainder. Why is this a problem? Why is this a problem? Think about contradiction. Think about contradiction. We defined r to be the smallest such integer that satisfies this. And yet we have found a new remainder that also satisfies this. That's r minus b. And r minus b is smaller than r. How can r be the smallest element in that set if r minus b is clearly smaller and still satisfies the condition of these sets?
It can't.
It can't. That's a contradiction. R minus b is a positive integer that is smaller than r. R can't be the smallest such integer then. Contradiction. Okay. That's a ion. All right. Does anybody have any questions? Yeah.
How does it make sense that it's b times q plus 1? How would it be the same?
So don't get too hung up. These are not set variables. They are just integers in the set. Basically, I'm saying that I'm not doing anything different. I'm making manipulations to change the form to show that there exists a smaller integer with these definitions, r minus b, that still satisfies the condition of this form. Okay, q was not a set thing. Q plus 1 was not defined as a set integer. It's just in the set. We're just saying that, look, if q is in the set, then q plus, let's say there's an arbitrary value q in the set. Then q plus 1 also exists in the set because this is accounting for all real integers q. Yeah. Any other questions? No questions? Okay.
So you win the whole number so I can see what you're trying to prove.
Yeah. You just proved existence. Now we're gonna prove uniqueness.
Okay.
So we've proved that for all integers, A and B, that they can be written in this form, right?
Do I have like a 2-minute summary?
Yeah, at the end of class I got you.
It's gonna be a video. No more.
So we've proved that existence is valid. What does that mean basically? That there will always be two integers. Go back to like division, right? When you divide, let's say like 8 and 3. Okay.
Your ampersand is backwards.
8 and 3. All right, 8 can be written as 2 times 3 plus 2, such that 2 is less than 3. Okay? And we basically just proved that that exists for all integers. Now we need to show that that case is unique for all integers. That means you can't write 8 as any other combination that works like that. I mean, you can write a like.
Well, I have a quick question.
Hmm.
Didn't you just prove that R must be less than B and greater than?
Yeah, I'm saying we just proved existence that this works for all integers in this form such that R is strictly less than B. Think about division. Can the remainder, when you're done with the long division step, right? And you're trying to figure out your remainder, can that remainder be greater than your divisor? No, right? Then you can, put it back in, subtract it one more time, reduce it, whatever. So we proved its existence for this form. Now we've got to prove uniqueness. Okay. Again, let's do proof by contradiction. So for sake of contradiction, okay, so let's let A equal BQ1 plus R1, and let that also equal to BQ2 plus R2, such that QI is distinct, or is a distinct set. Again, it's a fancy way of saying that Q1 and R1 are not the same as Q2 and R2. So let there be at least, if it's not unique, right? Then for contradiction, let's say there's more than one ways to write it. With the same conditions, okay? R2 must be less than Q2, R1 must be less than, R2 must be less than B, Q1 must be less than B. Okay?
Just to clarify, you said R2 is less than B and R1 is less than B?
Yeah, by definition, there's two ways to write this, satisfying this condition. Right? Okay, so again, algebra is going to help us again. Subtracting BQ2 from both sides yields B times Q1 minus Q2. And then subtracting R1 from both sides yields R2 minus R1. Okay. Let's go back to our definition of divisibility. It's kind of blurred out here. But what do we know now?
That Q1 minus Q2 equals R2 minus R1.
Yeah, exactly. There's going to be a connection between these two and this. So we know that R2 minus R1 is a multiple of this and a multiple of this, right? I want you to focus on the fact that R2 minus R1 is a multiple now of or sorry, of B. This is key. It's a multiple of B. That make sense? All right, let's make an inequality for R2. Knowing that Ri in general, all R has to be between 0 and 6. Okay. Now, what's the most this can be? R2 minus R1 for arbitrary values of R. How do you make numbers in subtraction? How do you make a difference big? You have a bigger number minus a smaller number, right? So what's the biggest possible value for R2? Sorry, not 6, B. What's the biggest possible value for R2?
B.
Right? What's the smallest possible value for R1?
0.
Okay, B minus 0, right? So on this side, it's going to be B. And notice I have it not equal to, but because this side, it can't ever equal B, okay? And now on this side, we want to do the opposite. We want to make the smallest possible number. So the lowest possible value for this minus this is going to be it's just going to be this times -1, which is negative B, right? 0 minus B. Does that make sense? Yeah. It's bounded in between this. Okay. So it's in between negative B and B, not inclusive. And it is a multiple of B. Correct?
Correct.
The only multiple of B strictly in between negative B and B, but not negative B and B, is what? 0. R2 minus R1 has to equal 0. What is that? What's true about R2 and R1 then?
They're equal.
They're equal. R2 equals R1. And if R2 equals R1, and if the B's are the same, right? The B and A stays constant. And now these two are now the same as well, right? Let's say they're both R1. So B Q1 plus R1 equals B Q2 plus R1. Subtract the R1s out, cancel out the B's, we're left with Q1 equals Q2. But then if Q1 equals Q2 and R1 equals R2, are these distinct representations? No. Yeah.
Can we also say if R2 is the same as R1, then R2 minus R1 equals 0, then B times Q1 minus Q2 Q1 minus Q2 would have to be 0?
Yeah, there are lots of algebraic ways that you could choose, but it's just one way I'm showing. Q1 equals Q2, right? Are these now different ways to write the same thing? No, they're the exact same thing. So we have now proved not only existence, but uniqueness. Any questions?
I think there's a certain notation which would cause this computation here to be quite a bit less long as it is.
Yeah.
It would be slightly more complex considering that some people in here may not have been introduced to set notation, but it would still be.
Yeah, set notation, we're not familiar with that yet.
But if you utilized an gated summation, you may be able to better denote R2 minus R1, assuming that they're not unique for sake of calculation. Okay, this is his last show.
Okay. Last big chunk is part 1 of Béziers theorem. Or Bézier.
It's pronounced Bezout.
Bézier.
It's not Bezout, it's Bezout.
Bezout.
I think it's, maybe it's French.
It is French.
What does he do?
That's a good guess.
It's very objective.
So you can report on this.
Specifically in integer.
So it's got two angles. Well, we can cover two angles.
Who's that?
I actually think you would go to a restroom with that glasses. So it's stopping you from recording.
No.
You were gonna watch
You know, as a reverse overset theory, you can check that computation. It will be correct.
That's it.
Does that say GCD
Really just
Your handwriting is,
In cursive.
Yeah.
Yeah, variables in cursive.
well, your wording is also.
Sure, okay, what is that ampersand? Why is it backwards? Why is it inverted?
Everyone knows that is.
Just try it.
that is.
No!
You're not being called
Don't you know how to write an ampersand?
Sure.
I swear to God, I'm gonna run out there and draw.
Sorry, you can also do what Ruark does, which is this.
Yeah, but you could also use Ruark's theorem, which is 0 times 2 equals
I only
1.
like to show.
Or 0 times.
He was asking me to read it to him because he can't.
Okay.
What is the?
Bayes' theorem. All right. So for any integers a and b, there exists such that they're both non-zero. There exists integers x and y such that ax plus by is the greatest common divisor of a and b. Okay. Okay. So it's relating linear combos of a and b to the common divisor. Yeah.
Could you leave that up for a while? They were messing around with my paper, so I need some more time to write this.
Okay. Yeah.
Give us the paper, dog.
All right. I'll give you guys a few minutes to write this down still.
That's the greatest one divisor. Yeah.
Sure, when do you think the lecture will be over?
In like 10 minutes, maybe max.
And how much repetitions after?
We can do that after this thing. is over.
Yeah.
A competition?
It
is-
seems to 3.
What is it?
No competition. I'll give you guys a few homework. I'll give you guys.
Yes!
Okay.
Can we get back to your lesson?
All right.
Wait, hold on, am I gonna have time to lecture today?
Yeah, no, bro.
Oh, we're leaving at 4:30.
Okay, but you spit all over my
Exactly.
paper.
I'm looking back to the next 10 minutes.
Workshop time.
I just wanted to.
Give me a thumbs up when you have this definition written down.
Yo, you're dead disgusting, bro.
I'm so sorry to be holding up the ground here.
How to create equal sign?
That's actually fucking disgusting.
I'm dying
sorry.
right now.
I had to spit all over it, dude.
I'm dying right now.
Everywhere.
He's over there.
You come to my class for 5 minutes and you're already disrupting. God.
Sorry.
Huh? What?
Sorry.
Ax plus by equals GCD of
A comma B.
Well, why? Yeah, I don't think it's. I was over back here.
I don't think. Yeah, okay, bro.
Well, why? I don't think it's me, bro.
This spot's like Jordan.
Awesome
It was so
sauce.
bad.
In my opinion, what are you
We're
talking
also
about?
gonna cover.
All right, we're gonna use a set again. Okay.
Are we gonna cover the inverse of these?
Maybe next time. All right, we're gonna move on. All right. Let there be a set S that is defined by this linear combo. I'm not gonna write the whole thing down. Huh. Who said? Did somebody say something?
I don't believe so.
All right, we're good. All right, let's again. Let D be the smallest element in this set.
Yeah, it's Z.
What are you staring at me?
Sound integer.
What do you want from me?
Okay, so D equals AX naught plus BY naught. Okay. Where X naught and Y naught are the integers that yield a smallest element D. Okay.
No, it's the value of the smallest value of D.
Wait, sorry. I'm tripping right now. Greatest common divisor is basically the biggest number that divides both B and A without leaving a remainder, right?
Base, yeah.
So how could it be a value greater than A?
No, D is not the divisor. Don't get it. D is just the smallest one.
Greatest common divisor right there, it says AX plus BY equals that. So wouldn't AX plus BY be greater than A and B? So how would greatest common divisor be equal to that?
It's not X and not Y.
Oh, B is an integer, so they can always be like -2. Like it can also be negative. Yeah, don't. Yeah. Anything else? Okay. Okay. Let's go back to our divisor algorithm. I call this part of the proof the plug and chug, okay?
Oh, yeah, plug and chug.
Oh yeah, plug and chug. So let there be A such that A equals D times the quotient plus the remainder. We know this exists because we just proved the divisor algorithm, right? So there has to be for some integer A and D is defined by this. There has to, this must be true for at least one case. No, for only one case because it's unique. Okay. When we substitute this for I'm sorry, I misspoke. A is the same A from this. Okay. But D can be written as AX naught plus BY naught times Q plus R equals A.
Sorry, could you repeat one more time what Q naught and what naught?
Yeah, they're the arbitrary values and that make AX naught plus BY naught are the arbitrary values and from this set that make D the smallest integer value of the set. Okay. Then we can write R again algebra as A minus AX naught minus BY naught Q. Some algebra is that A1 minus QX naught plus B times negative Y.
But it's like, it's just.
Are you sure?
Mhm.
Shift slightly to the left, please.
Yeah. My left, your left, your left.
Yes, sir. My apologies.
Okay.
I'll be leaving because of the meeting, yeah.
All good, all good.
Sorry.
All right. Now, what does this format remind you of? What does that format remind you of?
Are those
AX plus BY.
Yeah, AX plus BY, right? This is in the form of AX plus BY. That means this is in the set. This is part of the set. It's in the set S.
Are those Q's?
Oh, no.
Yeah.
Well, it's a Q right there for those.
My bad. I'll work on my penmanship or markermanship.
And work on how you choose to describe the understands.
Okay. So then R is also what? A linear combo. Linear combo of A and B in that set, right? It can be written in the form AX plus BY, right? Where X is equal to this and Y is equal to this. It's in the same form. Now R by the divisor theorem, R must be less than D, right? But D is the most minimal thing. We've defined D as the minimal, right? So that can't be true. So as a result, if it is smaller, the only value of R that is acceptable is 0. It has to be a number. It's a number smaller than D that's not integer, but D is the smallest integer. So it has to be 0, right? It has to be not non-integer because 0 is non-integer, right?
Wait, I thought D was the smallest integer in the set where A X naught plus G Y naught.
D is the smallest integer in this set, right?
Anything but zero.
So what would that mean? D would have to be less than Q.
Because of the divisor algorithm. Do you remember like A equals BQ plus R? And we just proved that R must be strictly less than B. It's the same thing. R must be strictly less than D. Okay, so R has to be less than D, which contradicts the minimality of D. So then R has to equal 0. But if R equals 0, then A equals DQ. And that means Q divides A. Okay? And we're running out of time, but if you do the same thing over again with B, then you'll see that D also divides B. D divides A and D divides B. And now next class, when we cover part 2 of Bezout's theorem, we're going to show why D is the greatest common divisor. But we've proved that D has to be a divisor. Okay. But yeah, that's all.
Considering the circumstances, that's actually substantially far into the subject of Bezout's theorem.
Yeah, it won't be too much. We've covered most of it. But any questions?
At some point in the future, we should also cover the inverse of Bezout's theorem. I think it would be quite advantageous for
All good?
its application.
All right, thank you. That's all.
Sorry, it's 4:15.
Sorry, are you weekly?
Huh?
You weekly?
Every Wednesday.
Yeah.
Every Wednesday.
Should I pause this? Sure, yeah.
223.
For Indiana, it's never.
Sharia. Should I pause this?
Yeah.
You stopping it?
Yes.
Hold on, before you, let me just make sure that it's not
Oh,
gonna
just
be,
click end stream.
it's gonna be saved, right?
Yeah, it's probably gonna be saved.